Welcome to our Introduction to Machine Learning lecture. And here in this session, we'll take a deep dive into the proof of the ordinary least squares regression estimator. So we'll look simply, I guess, at one, well, maybe not simply, but we'll only look at one slide. I guess technically it's about 2 or 3, where we will do together the derivation of the normal equations. So we'll derive analytically the optimal parameter estimators for our linear model under L2 loss. So this is what I had before when I introduced the linear model. So we said, hey, we're doing empirical risk minimization. For that, we are now computing for each data point in our training data set the prediction. We're computing the residual, so the sign difference, to the label at that training point. Then we are squaring it. And this we are now going to minimize in terms of this theta parameter vector here. And I told you that we can do that analytically by taking the first derivative, setting it to 0, and then solving this and recognizing that this guy here, this complete guy here is basically a quadratic function, and the derivative of a quadratic function is a linear function. And the linear function, if we set that to 0, we can solve for theta, and the result is this neat little compact formula here, which in statistics we call the normal equations. So no need for gradient descent. You can just numerically solve a linear system, which can be done quite efficiently for quite large data sets. So the derivation is not really difficult. Just want to do this together here with you so you can really check that you can do this yourself and that you can understand every single step of the derivation. Actually, we wrote down the derivation twice. We did this once in matrix notation and once without. So I guess I might start by doing it together with you with the matrix notation because, I don't know, it's actually simpler if you know how to do this. Before we do this, maybe let's start with our initial formula, so the least squares risk. So here again, we have our least squares risk. I explained this already here. So we have the prediction here. We have the true label here. And we now compute the residual. And I'll now simply assign a little symbol to the residual. So I'll call that epsilon I. So we can also do this in vector notation if we wanted to. So we can also say, hey, we can take capital X, so this guy here, times our vector theta. So we'll now take every row of the X matrix and take our theta vector and do this, right? So we multiply each row with the theta vector. So this is coefficient times feature value plus coefficient times feature value, coefficient plus coefficient times feature value, and so on. We add it all up, and this gives us the result of the first. This gives us the first prediction. So this gives us the y hat for our first observation, and we can do this for the second row times the theta, third row times the theta, and so on. And so we get all of our predictions here in a neat little column vector, and then we compute the difference between the vector of true labels, which gives us the vector of residuals, and we can now take the squared L2 norm of that, which is simply the sum of the squares. Okay, so far so simple. And like I said, I will not really discuss the difference now between p or p+1 features and with the intercept and so on. We'll just pretend it's we have just like silently dropped the intercept term and simplified our notation, as I've explained before. Now, what we can now do is we can start by looking at this column. So we'll use our neat little matrix notation here. So we now have this squared L2 norm for the vector of residuals. And what we want to do is we want to take the derivative with respect to the complete vector theta. And we can do that by simply expanding here our L2 norm as epsilon transposed times epsilon. Of course, that is the sum of the squared epsilons. And now we can take the derivative with respect to theta by invoking the chain rule. So this is a little quadratic function. So we can now do the chain rule by taking the derivative of this guy here with respect to epsilon, and then we do the derivative of epsilon with respect to theta. So let's look at these two things individually. So like I said, this is a quadratic function, right? In epsilon. So taking the derivative with respect to epsilon is simply 2 epsilon transposed, okay? Yeah, and here it depends a little bit what kind of I don't know, form of vector calculus you're using. So you have to sometimes watch out a little bit how to transpose stuff and so on. But yeah, I hope you are somewhat used to this already. If not, yeah, take a look at this again. So what we're using here is the so-called numerator layout. So now we can take a look at this guy here. So this is epsilon. What was epsilon again? So epsilon was simply our vector y of true labels minus the vector of predictions, which was capital X times theta, right? So, and we want now to take the derivative of this guy here with respect to theta. So, well, y is constant in theta, so we can just make that 0. And this is just a linear function, right? So this simply becomes minus x. And this is exactly what we have here. So now we can start reorganizing things a little bit. Well, I guess in order now to write it in theta, we should also write down what epsilon transposed is. So, well, luckily, fortunately, I already did that here. So I can write down, just copy this formula again here for the 2 times epsilon. So this is simply y minus x times theta. We have to transpose it because the original epsilon was transposed times our x. And we can simply now drop the 2 and we can drop the minus 1 here because, well, we can divide by them because it's an equation which equals 0. Now we can start expanding this guy here. So this will be, well, first of all, I guess we can transpose stuff. So the first term is y transposed. So we do y transposed times x, right? And then we do theta transposed times x transposed times x. And this is what we have here. So we now have these two guys. Now we can start distributing terms to 2 sides. So I guess we should collect everything that, or we could collect everything that contains a theta on the left-hand side. What I did here, we keep the rest, which is independent on theta. On the right-hand side, we can now transpose both sides. So we reorder, not reorder terms. We reverse the order of the terms and then transpose everything. So x becomes x transposed becomes x, theta transposed becomes theta, and here x becomes x transposed and y transposed becomes y. And now this rig looks solvable, right? If we now assume that our matrix X has full rank, we know that x transpose times x will have full rank, which means it's invertible, which means we can take the inverse, multiply both sides with the inverse, and we have finally arrived at our normal equations. I guess I don't want to read it out again for the left column. The left column is written down without vector matrix notation. It basically does the same thing. Taking the derivatives is a little bit easier. Then you have to do a little bit of extra work here to collect terms again, to kind of rearrange them again in vector matrix form, because we want to arrive at that at the end. So maybe do this, I don't know, as a homework exercise with pen and paper. I guess maybe try to do either the left column or the right hand side without looking at the slide and looking at this video. I hope that clears it up. So far until here.